Hello and welcome to this video on graphing a relation that's defined by an equation. Okay, so I have several examples here that are basically a combination of a couple of videos I've put up in the past on graphing an equation by point plotting, and also we're going to after we graph the equation, I'm going to also then state the domain and range of the relation given the graph of the equation. So in previous videos we've seen a relation. Okay, a relation is simply a correspondence between two sets where each element of one set is, corresponds or is related to an element of another set by some relationship. And we've seen those relations represented by a set of ordered pairs, a mapping or an arrow diagram, where you have a box for each set and then arrows, drawn from one set, elements of one set to elements of the other set if there is a relationship between them, and also as a graph. So here we're seeing our fourth major representation of a relation, and that is as an equation. Alright, so let me begin. So in each example I'm going to show today, I'm going to be asked to graph each relation, use the graph to identify the domain and range. So here's an equation, y equals 3x minus 8, where it describes a relationship between the variables x and y, right? Where x and y can represent real numbers we're dealing with here. So we're looking at a relationship between two sets of numbers. So as I did in my point plotting video, and what I'm going to do is make a little table. All right, we're going to make a graph, and a graph is again just a picture of solutions, right? We're going to see what values that x can represent correspond to what values that y can represent to make this a true statement, right? We're trying to find solutions to this. All right, so here's a table, and as I mentioned also in the point plotting video, if you want to look that up, or take a look at some other people's videos, or look in your books and point plotting, graphing equations. This equation is solved for y. You see how y is all by itself, and then the rest of it is on the other side, and no y, right? Just all in terms of x over here. So since it's solved for y, it would be easier to plug in values for x and then get the y value of the solution that way. So that's what I'll do. All right, so in my table here, plot, I have one column for values I'm going to replace x with, the second column for how is the y value going to be calculated, the second coordinate on my point, and I'll just write the equation, right, basically explaining how y is calculated. And then the third column, the solution to the equation, the ordered pair, where the x values first, the y values second. And if you recall, again, if you've been watching my videos on relations, this ordered pair implies that this value x from the first set corresponds to this value y from a second set of real numbers. Alright, and on my table here again I can plug in whatever I wish. I'm noticing that there's no denominator over here that I can make equal to 0, right? You're not going to be dividing by 0 over here, or taking even roots of negative numbers or logarithms of non-positive numbers, right? And other things that aren't allowed for real numbers. I'm not seeing any of that. So I can plug in really whatever I wish for x. Now I personally like centering my values around 0 on the x-axis, so I'm going to plug in the values -2, -1, 0, 1, and 2 and see what solutions I get from there. Alright, so when I have -2 for an x coordinate or an x value, you know, the way the y coordinate would be found would be just replace x with -2 in the equation. That's 3 times -2 minus 8. You do the multiplication before subtraction. So this would be -6 minus 8. It's -14. Right? So the ordered pair, right, that belongs to this relation is, -2 in the x on the x-axis corresponds to -14 on the y-axis, right? And then for -1 in the x, right, replace x with -1, y equals 3 times -1 minus 8. That's -3 minus 8, that's -11. And then the solution to this equation, what makes this a true statement, or an ordered pair that belongs to this relationship, this relation, -1 for the x, comma, -11 for the y value. Right? -1 corresponds to -11, or you could say that -11 depends on -1. When x equals 0, going through, y equals 3 times 0 minus 8. 3 times 0 is 0, minus 8 is -8. And there's the y coordinate, and the x coordinate 0, y coordinate -8. There's the ordered pair for that, the solution that belongs to this relation. When x equals 1, y equals 3 times 1 minus 8. 3 times 1 is 3, minus 8 is -5. Ordered pair that belongs to this relation, the solution is 1 for x, comma, -5 for the y coordinate. And then finally here, now you can plot as many points as you wish, right? You're trying to plot as many points as you can to the point where you start seeing a pattern on your graph. And hopefully after a couple of these you'll notice a pattern. I've pointed out before that if you're looking at an equation and there's no denominators and with variables, and all your variables in the numerators are to the first power, x to the first, y to the first, it's a linear equation. You're going to see these points falling on a straight line when we graph them in a second. And finally, when x equals 2, y equals 3 times 2 minus 8. That's 6 minus 8, -2. Right, so 2 for the x, comma, -2 for the y. And there's another solution. Now, I could do this all day long. Right? This is only 5 solutions to this equation. These are only 5 ordered pairs that belong to this relationship. But there are infinitely many. I mean, I could do this with all the integers, just plug in -3, +3, -4, +4. I could plug in any fraction, anything in between, any rational number, right? -1.5. I could plug in 0.785. I could plug in whatever I want. I can plug in irrational numbers like pi, square root of 2, and 0.0100100001. Just make up. You can very easily make up an irrational number, but really anything, and I could get a solution. Right? So these aren't the only 5. So as I mentioned in a previous video on relations, there are 4 major representations of a relation. I'll write those again here. All right, one is a mapping, or an arrow diagram, or just simply a map. Now, a mapping is great for relationships where there's only a finite number of relationships. There's not infinitely many ordered pairs. So this, I wouldn't necessarily make a mapping for the relation that's described by this equation, because what a mapping looks like, as a refresher here, you have one box involving the set of all the first value, where all the first coordinates are coming from, the x coordinates. So in this first box here, I could have -2 is there, -1 is there, 0 is there, 1 is there, 2 is there. But like I said, there are infinitely many. There are so many more. I put the little dot, 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 little ellipsis down here. And then a box on the other side involving numbers that might belong to the second, might be a second coordinate. In this case, the y values. And, there's -14, -11, -8 that's showing up, -5, -2. But clearly, as I said over here, there are infinitely many possibilities for my y coordinate. All right, I could have a y coordinate of -10 if I wanted. Just put in -10 for y, and you'd see that 18/3 would be the x coordinate, right? So the x coordinate of 18/3 in this box would correspond to -10 in this box. But I'm not seeing that yet. So I could put these 5 up, and then I have an arrow, showing the relationship. -2 corresponds to -14, -1 corresponds to -11, 0 corresponds to -8, and so on. 1 corresponds to -5, 2 to -2. But again, there are infinitely many. So this is very, it's not a nice, efficient way of representing a relation when there's infinitely many ordered pairs, infinitely many relationships. Alright, so that's, I can start a mapping like I just did here, great, but not the best one for this one. A second representation we've come across in previous videos, and I'll just recap here real quick. It's just as a set of ordered pairs showing the relationships between one set of numbers and another set of numbers. And they don't have to be sets of numbers either, but right now we're looking at 2 sets of numbers being related. So as a set of ordered pairs. All right, so this relation that I'm looking at here, has the ordered pair -14, right? Shows one relationship, which I see here in the mapping. Has another ordered pair, -1 to -11. Another ordered pair, 0 to -8. Another ordered pair, 1 to -5. Another ordered pair, 2 to -2. But again, that I'm a little ellipsis here. Again, this isn't practical because there are infinitely many, right? There's no way I can list them all. So again, a set of ordered pairs, the way to represent a relation that way, wouldn't be the greatest for a relation where there are infinitely many ordered pairs. I'd recommend this more for when there are finitely many, right? A reasonable, a nice, easy to see amount, all right, that you could easily list. All right, so these are all well and good. Right? You've seen these before, hopefully, or if not, you're seeing them now. But again, I'd reserve these for when there are finitely many ordered pairs. All right, then come what we're seeing on my page here. I'll get to the third representation is a graph, right, which we're going to see down here in a second. All right, now a graph, as I mentioned, is just a picture of the solutions to the equation, or a picture of the relationships. So that's where I'm plotting all these ordered pairs. I'm going to plot these points where the horizontal axis represents values from the first set, all the x coordinates. The vertical axis represents values from the second coordinates, the y coordinates. And the last representation, which I'm also seeing right here, is an equation. Okay, the last of the major representations we're going to come across for a relation is an equation, which I'm seeing here, that basically tells you the relationship between any value from one set and a value from the other set, and usually those values from these sets are represented by different variables. Okay. So let's look at these. Now I have the fourth representation here, y equals 3x minus 8. Wonderful. I'm going to do this third representation. Right, let's make a graph of this. Alright, so let's plot some points. Alright, so I've got the point, -2, -14. Alright, so I'm going to have each notch here. I have my x-axis and y-axis already set up. I'm going to have each each square represent 1 unit. Right, so this is -1. I remember how these are, they're just the real number lines, 0 in the middle here, and negatives to the left, positives to the right, negatives down, positives up. So here's -1 on the x-axis, -2 on the x-axis, right? So that's -2 on the x-axis, and then -14 on the y. So -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14, right? It goes a little further down than I deal with the little arrow there indicating that it's going down further. So this is still on the y-axis here. There's -14. And I'm plotting this ordered pair, right? This point that's in line with both of them. That's this location right here. And if you'd like to label it, put little ordered pair -2, 14 next to it, that's fine. Okay, so there's one solution to this equation, one ordered pair in the relation. Then I've got -1, -11, which I've already labeled, right? -1 on the x-axis, and then this -14, -11, right? 3 units up there on the y. And the location on the plane that's in line with both of those is right here. Great. Then I've got the ordered pair 0, 0 corresponds to -8, so 0 on the x corresponds to -8 on the y. So we are on the y-axis here with an x-coordinate of 0. All right, there you go. And you probably see it already that these ordered pairs seem to be forming a straight line. All these points are lying on a straight line on the coordinate plane. But let's keep going and see that that's really the case. The next ordered pair I have is +1, -5. So 1, -5, that's this location here. And then +2, -2, +2 for the x, -2 for the y. It's this location here. Alright, great. And again, you see these 5 ordered pairs I have plotted for the equation, y equals 3x minus 8. And it looks to me, and hopefully you're seeing this pattern as well, that, again, they're falling on a straight line. So, being that there are infinitely many points, right, infinitely many ordered pairs I could make, you can't possibly draw them all. You can't possibly point out each individual one. So what you do is, you lay out enough, graph enough till where you see a pattern, which I'm seeing here, this straight line, and then you draw on the rest. Right? You kind of, it's basically a very educated guess. All right, you draw on the rest. Where do you think the rest of the solutions are going? So I'm going to take my ruler here, line it up with these. It looks like all the ordered pairs fall on this. Right, so like this, and then go. And I would assume it would continue that way forever, because again, there's no real restriction on the value of I can replace x with. Same thing this way. I'm going to put little arrows on the ends because it looks to me I could plug in whatever I wanted for x. I could plug in -100 for x, and it would take me at some point way down, and I plug in 1,000 for x over here, and it takes me somewhere way up. So I'm going to draw the little arrows to indicate that the pattern seems to continue forever in both directions. Wonderful. So there's a picture of my relationships. Right, a graph of this relation described by this equation. Now comes the part with the domain and the range. Right, and I put up a video recently on finding the domain and the range of a relation. And as mentioned in that one as well, when you're stating the domain and range of a relation that has infinitely many ordered pairs, you're more likely going to have to use interval notation or set builder notation to describe the domain and the range. All right, so the domain of this relation, and for the domain you're looking at x coordinates. Right? For the domain you are looking at x values, first coordinates of your ordered pairs. All the what values in that first set correspond to values in the second set. So all the values in the first set on the x-axis here that actually correspond to some point, some y-coordinate. So you're seeing here that 1, right? 1 belongs to the domain because it has a point where it's an x-coordinate. 2 is an x-coordinate for this point. 0 is an x-coordinate for that point. -1 is an x-coordinate for that point. -2 is an x-coordinate for that point. And hopefully you're seeing that really every value on the x-axis would correspond to some point on this orange line I drew, or red line. Right? You know, if I said, how about -3.5? Well, you go to -3.5 on the x, there's a point down here somewhere that's on this line that has an x value of -3.5. So I could say that in words. If I say every value on the x-axis is an x-coordinate of some point, right? It corresponds to some value on the y-axis, then we would say that the domain is all real numbers, right? Because remember the x-axis and the y-axis, they're representing the real numbers. They're called the real number lines. But you could also write this in what's called interval notation. Now, when you write out interval notation, please remember you're going to write it in order from low number to high number, right? So on the x-axis, you're looking from left to right, and if you're talking the y-axis, you're going from bottom up. Now, for interval notation, there's like a left end, right? Well, there is no lowest value in the domain, right? I say -1,000. You could tell me -1,000,000, right? I say -1,000,000 is the lowest. Well, what about -1,billion? There is no lowest value in the domain. So to indicate that, we put a -infinity symbol, right? That indicates that there is no lowest value in the domain. Then a comma, and every value to the far left, indicated by the -infinity. Every value over here is in the domain up until all the way to the far right. Right? There is no highest value in the domain either. So to indicate that, we put a positive infinity, right, or just the infinity symbol after the comma. So this here indicates that every single number is in the domain. Every value on the x-axis has some point on this orange graph here that it's an x value for. And then on the ends of these, you cap them off with either a parentheses, or a square bracket, depending on whether or not those endpoints are actually part of the domain. They're actually part of a solution. And negative infinity and positive infinity, these are not numbers. These are concepts, right? So because they're not numbers, they're not real numbers, they're more ideas, they're not actually part of the domain. So you always have a parenthesis around infinity or negative infinity. Alright, so this is interval notation for all real numbers. But you also might have to write out what's called set builder notation. And again, I've addressed this in previous videos, so I'll do it a little more quickly here. Now we're talking about the domain. We're talking about values of x. So I can start off a set, right, little curly braces, and what's in the domain? Well, it's all the values of x such that, right, and then you put a little bar up and then a condition on that variable. It's all the values of x such that x, and here I'll just describe it. X is real, right? Because it's really anything, right? That's one way to put it. So you can do any of these three are fine. All of these describe the domain. The x coordinates of all my points is any real number. And I'm hoping you can see also that the same is for the range. Right? For the range, you're not looking at x coordinates here. You're looking at y coordinates. You look at the second coordinates, the second values in the ordered pairs in the relation, or the points on the graph. So what's in the range are any values in that second set that actually depend on values from the first set, right? Any values in the second set that are actually y coordinates of points on your graph. And here I'm looking bottom up, right? Low to high, bottom up on the y-axis. So we're seeing that, negative 14 is in the range, right? So it's the y-coordinate of that point. Negative 11 is in the range, negative 8 is in the range, negative 5, negative 2. Well, can you see that 0 is, and 1 is, and 2 is, and 3 is, right? Because they all, really everything, right? This orange graph, this line that I drew is going up and down in all, forever in both directions. So hopefully it's easy to see that every value of y is a y-coordinate of some point on this graph of this line. So the range is also every real number, right? The entire real number line, all real numbers. All right, so sorry about the clutter there, it's near the end of the page, but all real numbers. Or if you want to write that in interval notation, again, it's, this is the way to indicate in interval notation all real numbers. Every number from negative infinity to positive infinity, but again, those aren't numbers, but it's everything, just describing everything. This negative infinity again implies that there is no lowest value in the range, right? And the positive infinity simply implies that there's no highest value in the range, right? You can go up as high as you want. And if you're writing in set builder notation, right, with the little curly braces, now since we're talking range, the second set is coming, as these y coordinates. I'm going to use the variable y this time instead. It's what's in the range. Well, what's in the range is all the values of y, as long as y is a real number. Say such that y is real. Okay, and other graphs might have different conditions. Not every graph is going to have a domain and range that's all real numbers, but this particular one does. All right, we'll get into examples in a second where these are not always the same, right? Okay. So now that for the next couple of examples, I'm not going to do the mapping or the set of ordered pairs because again you're going to see that the relations have infinitely many ordered pairs, and a mapping and set of ordered pairs would be impractical. Alright, so here's another one. So I'm asked to, again, graph the relation, draw a picture of the solutions to this equation. The relationship between x and y is given, and again it's solved for a particular variable. Y equals x squared minus 8. And I'll point that out again here too, that if you're given an equation and you're asked to graph it, if you can solve for one of the variables pretty easily, I'd recommend doing that. It'll make making a table of values, a table of solutions, that much easier. If not, though, not every equation is going to be easily solvable for one variable. So if that's not the case, then just leave the equation the way it is and plug in a value for one variable, solve for the other, and find solutions that way. And it's not much different. But I think it's easier though. I think I would recommend solving for one variable like I have here. Alright, so here's y equals x squared, right? Notice the higher power on x here, so this is not going to be a line. Y equals x squared minus 8. So solve for y, so I think it would be easier to choose values for x. Again, right, so again I'll make a little table. Right, values of x, and then this is the y column. And I'll also put in the equation of how are we calculating that value of y. And then the third column, the solution, the ordered pair with the x coordinate first, y coordinate second, the solution to this equation that we're going to plot, or an ordered pair that belongs to this relation. And I'll plug in the usual values that I do. Negative. You can do whatever you want, right, as long as you're not dividing by 0 or doing something that you can't do with real numbers. You can plug in whatever you want, so you don't have to use these 5 that I like using. And and if for some reason I don't see a pattern after these 5, I'll plug in more. Right? You just keep plugging in values, you keep finding solutions, keep plotting points until you see enough of a pattern to say, I get what the graph's doing right now. Alright, so when x is negative 2, Now remember, this is x squared, so you're squaring the negative 2. That's negative 2 times negative 2. That's positive 4 minus 8 would be negative 4. Right, so you have ordered pair x coordinate negative 2, y coordinate negative 4. This here, again, you're squaring what x is, right? And x is negative 1. So negative 1 squared is negative 1 times negative 1. That's positive 1 minus 8 will be negative 7. So negative 1 for the x, negative 7 for the y. 0 squared minus 8 is just negative 8. So you have 0 for the x, negative 8 for the y in that ordered pair. 1 squared minus 8 is again negative 7. 1 minus 8. So 1 negative 7. And 2 squared minus 8 is again 4 minus 8 or negative 4. So you have the ordered pair 2, negative 4. Okay, so I'm going to plot these 5 points. And again, you can plug in whatever you want. You can plug in fractions, plug in stuff between these, larger numbers, smaller numbers, whatever you want, and find other solutions. Okay, great. So here's my equation the equation representing the relationship between two sets of numbers, x and y. Now let's make a picture. All right, let's make a graph. All right, so the first point, and again, I'm going to have every square represent just one unit. Right? You can, as long as you're consistent, right? If you have every square on the x-axis represent 2 units, stick to that. And you can then have every square on the y-axis represent 4 units if you want, as long as you're consistent with your axes and labelings. So negative 2 for the x, negative 4 for the y. I got a negative 4 on the y-axis, and that would be this point right here. That's in line with both of them, this location. Great. Then negative 1 for the x, negative 7 for the y. And there's negative 1 on the x-axis, negative 7 on the y-axis. There's that location. And you're not going to be able to tell too much from just 2 points, right? Some people accidentally think, oh, this is going to be a line again, right? Because you got these 2 points that are falling in a straight. Well, any 2 points fall in a straight line, all right? And again, with some practice, you'll be able to tell that, oh, one variable is to the first power, the other variable is squared. That's not going to be a line, right? Just from looking at the equation. It's going to be something called a parabola that we'll see in a second, a little U shape graph. 0, negative 8, 0 on the x, negative 8 on the y. And right here is where we're seeing these do not fall in a straight line. Right? If I were to draw a straight line through these two, it wouldn't hit that third point. Same thing if I drew a straight line through these two, it wouldn't hit that third point. So it's right away, now we're seeing this is not a straight line graph. The next point, 1 for the x, negative 7 for the y. That's this location. And finally, well, again, we can plot more. 2 for x, negative 4 for y. That's this location. All right. Again, you can put in other ones. I might as well put in some other ones. How about if I put in 3 for x, and I'll just say this one. 3 squared is 9, minus 8 is 1. Right, so positive 1 for the y. 3 for x, 1 for y. There's the ordered pair, 3, 1. And the same would go for negative 3, wouldn't it? Right? If I put in negative 3 for the x, that'd be 9 minus 8 again, positive 1 for the y. Here's some other points. And again, you can keep going. So I'm seeing this like U-shaped pattern here. Now, this is called, as I mentioned before, a parabola. I'll just connect the points. And again, now I'll say this right now too. When you're drawing a parabola, that point at the bottom called the vertex, that point that like is in the middle here between the two halves, it's not pointy down there, it's more curved. So try to make it more curved when you're drawing it, don't make it sharp. And then we'll connect these points, and now it would seem to me that it would just keep going up on both directions, right? If I plugged in 4, you could plot another point if you wanted. 16 minus 8 is 7. I'm sorry, 16 minus 8 is 8. You'd have 4, 8, and then negative 4, 8, and then plug in 5. 25 minus 8 is 17. And it looks to me, based on just a few other points, that it's going up forever in both directions. Getting larger, you're getting larger and larger y coordinates the further right you go and the further left you go with your x coordinates. So I'll put little arrows up there to indicate going up forever. All right. Great. There's a picture of my relation. All right, that's described by this equation here. And now we're going to state the domain and the range. All right, so I'm not going to do all three like I did in the previous example where I write out in words and in interval notation and in set builder notation. I'm just going to do interval notation. So domain, remember you're looking at the x-axis. What values on the x-axis actually correspond to values on the y-axis, right? What values in the first set actually correspond to values in the second set. So negative 3 is in the domain, negative 2 is, negative 1 is, 0 is, 1 is, 2 is, 3 is, 4 is, 5 is. And hopefully you're seeing that everything in between those is also in the domain. Negative 2.5 corresponds to that point. 3/4 corresponds to some point down here on the graph, right? And go to 5,000. This is going up forever this way. So 5,000 even, would have a point way up there, way up and up. So you could pick any x value, and it is going to correspond to some point on this green graph, this parabola. So again, there is no lowest value in the domain. There's also no highest value in the domain. The domain is again all real numbers. So it would have this interval notation, right? Everything from negative infinity to infinity, indicating there's no lowest and no highest value in the domain. Anything you want. All right, now it's the range that's different this time. All right, the range, right? Remember, we're looking at y coordinates, y values. So what values on the y-axis actually depend on values from the x-axis. Right? What y values on the y-axis are actually y values of points on the graph. So from this picture, I'm seeing negative 8 is the y coordinate of a point, and that is the lowest one. Right? There is no negative 9 isn't. There's no graph down here below negative 8. Negative 8.5, negative 8.2 even, negative 8.01 isn't. Negative 8 is the lowest y value in the range. And then negative 7's in the range, right? Negative 4, we see that 0 is, we see that 1 is. 2 is in the range because it's, the y coordinate of this point. 3 is in the range, it's the y coordinate of this point and this point. And, really, anything you see above negative 8, right, go from negative 8 up, every single one of those values is going to be the y coordinate of a couple points on this graph. All right, so how do I write that in interval notation? That's all the numbers from negative 8 upward, negative 8 and larger. Well, negative 8 is going to be my left end of the interval. It's there is a lowest value in the range this time, and it is negative 8. So not negative infinity, right? It's like I turn this sideways, right? Flip. But negative 8 is the lowest value in the range, and there is no highest value, right? It's everything from negative 8 upward. So to indicate that, that's from negative 8 all the way up forever. Again, when there's no highest, it's again positive infinity. Now on infinity, right, I mentioned earlier, always a parentheses to indicate that it's not a solution, right, or not part of the range. Infinity is not a number. But negative 8 is part of the range. You see, negative 8 is the y coordinate of this point here. There's 0, negative 8. Negative 8 depends on 0. It is part of the range. So to indicate that one of these endpoints is part of the set, you put the square or rectangular bracket, right? Instead of a parenthesis, make it little 90-degree angles here. And that little rectangular bracket indicates that, again, -8 is part of the range. So this is every number on the y-axis from -8 upward, -8, and anything larger than -8 is in the range, is a y-coordinate on this graph. Great. All right, and then I just have one last example where we flip the tables a little bit. It's an example where instead of y being solved for, x is solved for. Right, so here's again another relation, right? A relation that's described by an equation between values on the x-axis and values on the y-axis, and the x is equal to y squared plus 1 is the relationship this time. Alright, so this time you see how the relation, the equation representing the relation is solved for x. X is alone. So I feel like when I'm making my table, it would be easier to plug in values for y. So this time I'm going to have a column for values for y I'm going to pick, and then a column for the values of x that correspond to that value of y. And how we calculate, I'll just put in the equation. Here's how we're calculating the x. And then the ordered pair. Now don't forget, the ordered pairs come in this order, right? X coordinate first, y coordinate second. Alright, it's values on the x-axis corresponding to values on the y-axis, or values on the y-axis depending on values on the x-axis. So we'll see the ordered pairs in the relation over here. Alright, and as before, I'm not seeing any denominators with variables, or any even roots or logarithms, or I'm not seeing anything that would restrict my use of the real numbers. So I'm going to plug in my usual -2 to 2, -2, -1, 0, 1, and 2, and see what happens, see what it looks like. And you don't have to do these 5. You can do some other 5, or maybe even 7 or 9 points if you're if you're unfamiliar with things. All right, let's see what happens. So this is when y is -2. Right, so x equals, replace y with -2, and this is -2 squared, or +4 plus 1. That's 5, +5. So now be careful when writing the ordered pair, right? The x-coordinate is +5, so 5 in the first position there, and the y-coordinate, the one I plugged in, that's the second position, the -2. And so in this relation, +5 corresponds to -2. When y is -1, so x equals -1 squared plus 1, that's 2, right? 1 plus 1 is 2. So again, be careful. 2 is the x-coordinate, -1 is the y-coordinate. I'm just going to write these out. Right? Now, when y is 0, 0 squared is 0 plus 1 is 1. So I'm getting 1, 0, 1 for the x, 0 for the y. When y is 1, you get 1 squared plus 1, which is 2. So 2 for the x, 1 for the y. 2 comma 1 is the ordered pair in the relation. And when y is 2, x equals 2 squared is 4 plus 1 is 5. So I'm getting 5 for the x, +2 for the y. All right. So again, just 5 solutions. There are only 5 ordered pairs out of the infinitely many. All right. So because there are infinitely many, again, not going to make a mapping, not going to make a set of ordered pairs. I'm going to draw a graph, right, from an equation. All right, so here's the ordered pairs here. Let's plot these points. So I got my axes written out, and again, I'm going to have each square represent 1 unit. All right. So the first order pair there, I've got 5 on the x corresponds to -2 on the y. So here's 5 on the x, -2 on the y, and that's this location. Then 2 on the x corresponds to -1 on the y. Alright, that's this location. So I got 2 solutions now. Then 1 on the x corresponds to 0 on the y, which is in the middle there. So the y coordinate 0, meaning I'm going to be on the x-axis. Right? There's 1, 0, 1 comma 0. And now we're seeing that it's not a straight line. Right? Keep going. 2 on the X to 1 on the Y. Got the ordered pair 2, 1. And finally 5 on the X to 2 on the Y. Got the ordered pair 5, 2. There we go. And can you see the parabola shape again? But this time the parabola is, opening to the right. And I'll draw that in. All the ordered pairs look like all the solutions look like they're going to be following this pattern. And as with the last example, if I plugged in 3 for Y over here, if I plugged in 3 for Y, I'd have 3 squared plus 1, that's 9 plus 1, 10. You'd have 10 for X, so you'd have 10 for the X and 3 for the Y. You'd have this location. Same thing for negative 3. Right? You'd have 10 for the X, negative 3 for the Y, this location. And it just looks to me like this just keeps going up and up and up. Right? It keeps getting higher and higher and higher. And then down here, this keeps getting lower and lower and lower. Right? So this is going up forever. This is going down forever, getting lower and lower, as low as you wish, as the further out you go. Great. So here's a picture of this relationship, just showing where these infinitely many ordered pairs are. And then now that I've got this picture drawn, let's state the domain and the range. Right, so again, the domain and range, you can write it out in words, or with that set builder notation with the curly braces and the bars and all that, and the conditions on the variable. But again, I'm gonna just stick to my interval notation here. All right, so the domain. Remember, you're looking at the x coordinates. What values in that first set, what values on the x-axis actually correspond to y values in the relation that's described by this equation, or what are actually x coordinates on my graph here. Well, looking at this graph and the x-axis, you see how the number 1 is the lowest value on the x-axis that is actually an x-coordinate for a point on this graph. Right? 0 isn't on the graph. Right? 0 isn't an x-coordinate. Negative, even 3/4 or 0.99 isn't. 1 is the lowest. Nothing to the left of 1, nothing below 1 is an x-coordinate for a point on this graph. So 1 is the lowest value in the domain. So I put 1 comma, and then 2 is in the domain, right? It's an x-coordinate for these points. 5 is, 10 is, 3 is, 4 is, 6 is, 7, 8, 9, 2.5, 3.5, everything in between. Hopefully you can see that everything from 1 onward, every x coordinate, every x value 1 and greater than 1 is part of the domain for this graph, for this relation. So that would indicate that is from 1 to infinity. Right. Again, this infinity just indicates there is no largest value in the domain, and we have everything above 1 in the domain, right? Everything above 1 in the domain, and there is no largest value. And you always cap off the infinities with a parenthesis, indicating that it's not part of the set, right? Infinity is not a number; it's just an idea. 1 though, right? Like the previous example, this end here, the number 1 is in the domain, right? 1 is the x-coordinate of this point, 1, 0. So I indicate that 1 is in the domain with the square brackets here. All right. Great. So there's the domain, all the numbers greater than 1 and equal to 1. You could write that as an inequality as well. I guess I will do the set notation here. This would be in set builder notation. I would say the domain is all values on the x-axis as long as such that x is greater than or equal to 1. Right? The little condition describing what values on the x-axis are actually part of the domain. Right? This is 1 or greater, which I'm seeing in the picture. All right, and then for the range, again, I'm looking at the y-axis. What values on the y-axis actually depend on values from the x-axis, are actually the y-coordinate of some ordered pair on the graph. Well, we're seeing 0 is a y-coordinate, 1 is a y-coordinate, -1, -2, -3, 2, 3, 4, 5, 6. And the fact that this is going up forever and this is going down this way forever shows me that every value on the y-axis is a y coordinate of a point on this graph. So the range is all real numbers. So you can write out all real numbers, or the interval, the set builder notation, where all y values such as that y is real. But again, I'll put in this interval indicating all real numbers. That's everything from -infinity to infinity, right? There is no lowest value in the range. There is no highest value in the range, and every single number you think of, every number on the y-axis is the y coordinate of some point on the graph. Wonderful. All right, so hopefully that gave you just a few examples. Hopefully it's easy enough to take an equation, plot a few points, plot enough points to where you're seeing a pattern and can make a reasonably educated guess as to what the rest of the pattern looks like. And then once you've graphed the rest of that pattern, once you've graphed the equation, drawn a picture of the relationships, then hopefully from there it's also simple to state the domain and range, what x coordinates are used, what y coordinates are used. All right. And as always at the end of these, I like to say, try your best, do the best you can to try to understand and get the material beforehand, before you go looking for help. Read the material, of course, read through the author's examples, perhaps even try to work out solutions to an author's examples before you see how the author did it themselves. See if you can learn from any mistakes there. Practice exercises, practice problems, look for solutions if they're available to as many as you can so you can check yourself. And don't just give up after the first attempt. Don't be so easily frustrated. If after this first attempt doesn't work out, try it some more, and if after several attempts you're still not getting it, still not working out for you, then perhaps you should read the material again, maybe even a third time, because who knows, maybe on a second or third read through of the material you'll catch something that you didn't the first time. Something will click on the third read through maybe that didn't click the first time, and it'll make working through the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not getting it, it is not a sign of weakness whatsoever to go looking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone in the class that knows the material well and is willing to help. Look for supplemental materials online. There's lots of it out there. Look for videos on the subject that you're trying to study, like maybe this one, or plenty of other videos out there that are superior to this one. I assure you can find them. There are plenty out there. But just keep at it. Stay persistent. Keep practicing, and also try to have a positive attitude. That's the hardest part, I think. A lot of people tend to say they hate math. I hate math. I hate math. I've always hated it. It's always been a struggle for me. Well, if you go into it with that mindset, thinking that you hated it, you're probably going to continue to hate it, and it's going to make learning horrible. Just try to have an open mind this time. Next time you work on things, try to think, I'm going to enjoy learning. I'm going to enjoy this. Something's going to come out of it. I'm going to try to have fun, and try to keep a positive attitude. And don't give up. So just stay persistent, keep practicing, try to have a positive attitude, try to have fun, and I just know you'll get it eventually. And thank you for watching.